My name is Dylan Brown, and today I will be presenting my controller design for a DC motor control. The DC in DC motor stands for direct current. A DC motor's main purpose is to convert direct electrical power into mechanical power. To do this, a permanent magnet known as a stator is used to provide a constant magnetic field. This, coupled with an armature, which is a metal coil that rotates, and a DC power source, provide the motion. Current flows through the system, which due to the magnetic field causes the coil to rotate. The rotation of the coils can be linked to a shaft, which gives mechanical motion to a system. Therefore, you have your mechanical power. So in this project, I modeled an armature-controlled DC motor. The motor and shaft are assumed to be rigid. The friction torque is assumed to be proportional to the shaft angular velocity. At the shaft itself, the torque is proportional to the current through the applied voltage, or VA, in the model. The applied voltage is the single input and the angular velocity is the single output. The system equations were gathered from the system model. The left side shows the electrical side equations with the current with respect to time, and the right side shows the mechanical side equations with omega with respect to time. Here are the transfer function in the state space model. The state space model comes from the system equations on the last slide. The state space model was actually used to determine the transfer function by using matrices. The equation is C times Si minus A to the negative 1 times B, and if you do that, that gives you your transfer function of K over JL S squared plus RJ plus BL times S plus RB plus K squared. So here are my system parameters. To get these, I just Googled system parameters for a DC motor. These specific values are for a C23-L45 DC motor with a winding code of 30. This motor comes out of an online catalog at moog.com. It was just the first one that popped up, so I went with it. The parameters themselves, the moment of inertia, or J, is 0.000037. The viscous friction constant, or B, is 0.19. The force/torque constant, K, is 0.04. The electric resistance, R, is 3.27, and the electric inductance, or L, is 0.00426. So my design requirements. The controller was designed for a 12% overshoot, a settling time of less than 0.4 seconds, and a steady state error of 0. The way I got these requirements were I just pretty much made up some random numbers and went with it. As you can see from the picture on the screen, the original open loop system performed well. It met the 0.4 second, but it did not meet the 12% overshoot requirement. The open loop had a final steady state value of 0.0603, a rise time of 0.0042 seconds, and a settling time of 0.00493 seconds. Since my open loop controller design did not meet all the design requirements, it failed to meet the 12% overshoot, I decided to add a PID controller. The PID controller successfully met all design criteria. So the picture on the screen shows the closed loop PID controlled system. For the closed loop response with the PID controller, the final steady state value was 1, the rise time was 0.0042 seconds, and the settling time was 0.00121 seconds. And as you can see, it meets all the criteria. It stays out of the yellow. So this is my compensator editor view that shows the final equation that I got for C. I had to include 2 real zeros in there in order to account for the overshoot and to do the PID controller. My final C is 1 plus 0.00027s times 1 plus 0.00061s, all divided by s. And you can change the the number in there to make it quicker or slower. So in conclusion, it worked. The PID controller met all design requirements and it was a success. So these are my references. The top link takes you directly to the PDF of the catalog for the DC motor. Wikipedia and Learning Engineering were just references for me to learn more about DC motors and kind of the way they work. All of the programming and MATLAB code was all learned from the examples given in class and on Blackboard.